Do you feel the vibes?
Okay, so like I said, everything we've done until now, right, has been on the rectangular coordinate system. So basically you have an x-axis and you have a y-axis, and they're perpendicular to each other. And everything we've graphed has been along that, right? So what is the rectangular coordinate system? It's basically a two-dimensional system that gives you a location, right? X comma y. And that coordinate, that location, is basically a description of how to get to that point from the origin, right? So if I say 5 comma 7, you know to go over horizontally 5 spaces and go up 7 spaces. It's like an address, and you find the point. Okay. Now, the polar coordinate system is a two-dimensional coordinate system as well, right? We still have 2 dimensions, but each point on the plane is determined by a distance from a fixed point and an angle from a fixed direction. So there is still a little bit of an address, right? But it's determined by a distance from a point and then a direction. So for example, to get to this point, right, I would say, okay, start here, go over, let's say 5 meters, and then rotate by 30 degrees, and you'll get to that point, right? So go over, 5 meters, rotate 30 degrees, and you'll get to that point. So again, it's an address on how to get somewhere, right? So you can imagine, right? We don't live in a rectangular realm, right? We live in like a spherical universe, right? So it's really hard, like for example, like if you're out, in space, to say, okay, go this much and then hang a left at like the next star or something, right? It's easier to describe everything in polar coordinates, right? Even like for airplanes and everything, it's so much easier to describe that way, right? Because if you're flying an airplane, again, there's not a 7-Eleven up in the air where you're like, okay, go up to the 7-Eleven and then make a right, right? That's not how it works. So all of these are better off given in polar coordinates. Okay, so in a rectangular coordinate system, by the way, this is also called the Cartesian coordinate system after, René Descartes. In a polar coordinate system, as opposed to X and Y, our variables are now R and theta. So go out a certain radius and then rotate a certain angle theta, okay? So we kind of have to forget everything that we've known. Okay, the origin, right? Here we have the origin in the Cartesian coordinate system. In the polar coordinate system, we have the pole. That's the origin. That's where it all starts, the pole. And then this 0 axis, right? That's the polar axis. And then from there, we rotate. So again, the origin is called the pole. The polar axis is a ray that extends from the pole. And then polar coordinates are R and theta. R is how many, the distance that you go away from the pole. Theta is the angle from the polar axis OP. So to graph a point, all right, in polar coordinates, if you have a positive value of theta, means you go counterclockwise, just like before from the polar axis. If R is positive, P lies on the terminal side of theta. If R is negative, P lies on the opposite ray of the terminal side of theta. Okay, so for example, suppose you have, a radius of 3 and theta is 30 degrees. Okay, so here's the polar axis, right? From the polar axis, you rotate 30 degrees, right? That's the ray that you rotated, correct? If your radius is 3, you go 1, 2, 3 units out, and that's where your point is. Now, suppose your radius is -3 and you're at 30 degrees. Again, from the polar axis, you rotate 30 degrees. Okay? But now, if the radius is -3, on this ray, you go in the opposite direction 3. So 1, 2, 3, and it'll be here, the point. Okay? So you go in the opposite direction, huh? It's exactly it. And so there are, right, so if you added 180, it would give you the same. If you want to keep the radius the same, right, positive value, but add 180, exactly. That's what we're going to do right now. Okay, so just like, so rectangular coordinates are graphed on a rectangular grid. Polar coordinates are graphed on a circular or a polar grid, and that's what it looks like, right? That's, so no more Cartesian. You're going to forget about that. That's what it looks like. Doesn't that remind you of, what does that remind you of? Wait, what? Okay, yes, nerds, but what else? I was going for, you guys are so trained for, I was going for like radar, like in movies. You know how like when they show like radar, you guys are like, okay, unit circle, right? Like when you watch movies, doesn't that look like a radar? Huh? It looks like one of those radar circles. Oh. It looks like the one from exactly. Okay. Or any other movie where they're tracking something on like, that one, yeah. Like very right. Okay, so here we go. 3 comma 4 pi over 3. So from here, we rotate to 4 pi over 3, which is down at the bottom here. And then we're going to go 3 units out. So each one of these, right, each one of these concentric circles is 1 unit, right? And so you go out 3 units, so that's where it is. So it's just a point, huh? Okay, so you're going radially out. So here's what you do. You start from 0, you rotate to 4 pi over 3. Now you're here. And now from the pole, you go out 1, 2, 3. Okay? If it was negative, it would be on the pi over 3 line. You would go 1, 2, 3 this way. Okay? If it was negative, you would go here. Okay? Yeah. Okay, so here we are at negative 240 degrees, right? So that's your theta, negative 240 degrees. So where would that be? At the 120, but now it's negative 2. So at the 120, I'm going to go 1, 2. So it'll be right here because it's negative. Okay? Maybe I should, okay? Right? So the 120 mark, I'm sorry, the negative 240 mark would have been that. That's the terminal side. Now you want to, because it's negative, you want to be on the negative ray, okay, on the opposite ray of the terminal side. Okay. So take a look here. You have 2 and then 70 degrees. So you go out 70 degrees, right? That's a little bit past the 60. And then 1, 2, right here. Okay, now, this one is 2 and 430. So you're going to go to 360 and then how much more? 70. So right here. That's the same location, correct? Because what have you done from the original point? You added 360. Now, 2, negative 290. Where would that be? Oh my God, at the 70 again, right? So what have we done now? Minus 360 from the original, right? So what does that tell you? If you have theta and you do 3 plus or minus 360, or if you do theta plus or minus 2 pi, that gives you the same position if you keep the radius the same. You all know this, right? Okay, so here, 3 comma 50. So we go over to 50, which is right over here, and we're going to go out 3, 1, 2, 3. Here. Okay, This is negative 3 and 230. So 230 is where? Right over here. But now negative 3. So look, that would have been the ray. Negative 3, it goes on the opposite ray right here. Is that the same position? Right, so what have we done here? We made R negative, and then we did theta plus 180. So that combination together make R negative. That's what Torah was saying before. And, you know, a 180 difference, that's what that does. Okay. Negative 3 and negative 130. So negative 130 goes where? Right after, right. And then, so this is the ray, but now it's negative, so we go back here. Same position, right? So what have we done now? We did negative R, and then we did theta minus 180. So same situation. So if you have negative R, theta plus or minus 180, or negative R, theta plus or minus pi, you also get the same position, okay? And this is a summary of exactly what we said. If you have R and theta, then this or this gives you the same position, okay? Remember that. Okay, so now let's apply that. You want to find 4 different pairs of polar coordinates that name the same point S. S is right here if you can't see it, right? Between negative and positive 360. So what would be one of them? One is just the most basic, right? That's 210 degrees and 1 unit out. Right. Negative. No, it's 1. Is it 2? Oh, it's 2. Sorry. Oh my gosh. Okay, so then negative 2, and then we do 210 minus 180. So that would be negative 2 comma 30. What else can we do? Right, so we can do negative 2 and then 30. Okay, hang on. Let me do the other one first. We can do 210 minus 360. And then we can do negative 2 and negative 330, right? Okay. So basically you can take this one and subtract 360. You can take this one and subtract 360. Okay? All right. So on the test, I'll probably ask you for like 2 or 3 or however many of these. Huh? Yeah, that's the first one, right? But we want it to be between 360 and negative 360. Yeah, otherwise you could go like infinitely, right? Okay. So graphs of polar equations. Let's talk about polar equations. So on the coordinates, so all we've done is basically learned how to graph similar things to coordinate points like 3 comma 4, negative 7 comma 5. That's all we've done so far. So what about equations, right? In polar coordinates, in rectangular coordinates, when you have x comma y, you'll have equations like y equals 3x plus 2, right? So when you have that, you know that, when x equals 0, y equals 2. When x equals 1, y equals 5, and so on and so forth, right? That's how we first learn how to graph linear equations, right? On the rectangular coordinate system. So let's do a similar thing here. Let's find all of the points that satisfy an equation just like we learned how to do back when you were first learning how to graph, right? So because right now you're like in the algebra 1 phases of the polar coordinate system, right? So the equations in this are going to look like this. r equals 2 sine theta, right? So your independent variable will be theta, and your dependent variable will be r. So just like we plugged in values of x, here we'll plug in values of theta and we'll generate our graphs. Okay, so here we want to graph a polar equation that satisfies this, a graph that satisfies this equation, r equals 2.5. R equals 2.5, okay, if theta is, let's say, 0, r equals 2.5 would be this, okay? If theta equals pi over 6, r equals 2.5 would be that. If r equals pi over 2, if theta is pi over 2, r equals 2.5 would be that. What if theta was 5 pi over 6? R equals 2.5, right? Here, r equals 2.5. Go over to the other angle. What is this going to trace out? A circle, right? So if you do it numerically by picking points, you see that maps out a circle. If you think about it logically, you want a graph that is radially out from a given point of 2.5. Isn't that the definition of a circle? Right? In geometry, we say a circle is the set of all points equidistant from a center point, right? So when you have r equals a constant, that just maps out a circle of that radius, right? Okay, so theta equals pi over 6. No, theta equals 5 pi over 6. So for all values of r, theta equals 5 pi over 6. So when r equals 1, theta equals 5 pi over 6, and so on, right? And then if r is negative 1, that's what it looks like. So when you have theta equals a value, it just maps out a line. Isn't that cool? That's actually pretty cool. All right, so this is how I used to do my, before I started out with lesson plans, this is how I used to do all my assignments. So this is actually what you're going to have. This is going to be actually assignment number, what did we say? How much? 40. Oh, yes, this is homework number 40. I'll tell you. I'm going to give you guys graph paper. And I'll also, on the topics page, I'll put like a page of polar graphs, okay?
Press start.